All right, so to start off this year, or this quadmester, I guess I should say this year so far, we've done distance and displacement, speed and velocity. We did acceleration. In all of those days, what we looked at were motion equations because, I mean, distance and displacement are talking about your movement. Velocity is talking about the rate of your movement, and acceleration is talking about the rate of your movement. So now, what we're going to look at now is motion equations, because even though we did look at several motion equations, there's many others. And hopefully you've printed off of Google Classroom or off the website my motion equation sheet. I highly suggest printing that off for homework, for lessons, for the test, clearly, which is on Friday. Again, test is on Friday, which will be on everything we've done so far. All right. Again, more details to follow. All right, so getting into our motion equations. Again, one of the reasons that I think you should have the motion equation sheet in front of you, because a lot of students struggle with which equation do we use? And that's something that I go through right now. All right, so our first lesson, or our first example, we have an Olympic, and again, word problems. I find with any time of class, word problems are tough. Because you're mixing, in physics, you're mixing math and English, which is never a good thing for most people. All right, so I'll look at, because I was a person who was terrible with English, good in math, so I'll share my strategies of how I get across or get through word problems. The first thing I do is read it. All right, so to get a picture of what's going on. So I'm looking at my example here. An Olympic speed skater begins the race and accelerates at a rate of 2.5 meters per second squared forward, I hope. How far has the skater traveled after 5 seconds? Okay, so I've got the picture of what's happened. We have an Olympic speed skater, they're accelerating, and I want to know how far they've traveled after 5 seconds. All right, so what I want to write down is what information do I know and what information am I trying to find out? Okay, so the first thing is the Olympic speed skater begins the race and accelerates. Well, I know that is my acceleration. So I'm going to write that down. I got 2.5 meters per second squared forward. So I'll put an F for forward. All right. How far? So right away, I'm looking for my delta D. All right. Has the skater traveled after 5 seconds? So delta T, or T, they're the same thing, is 5 seconds. Now, what you have to watch in physics questions, and this will come up quite a bit today, is sometimes there's secret variables that are written in the question that you have to think of actually what is happening here. Does anybody know what might be a secret variable here? Because there is one that we haven't got that is in part of this question when you read it. Can anybody catch the secret variable that we know? And what I mean by variable is, well, we have A, we have D, and T. Those are all variables we know the values of. Well, we don't know D, but we're going to find it. Anybody know? Because we have an Olympic speed skater begins the race. What speed are you moving at when you begin the race?
0.
0, unless you're going to get disqualified. All right.
So
VI of 0. And again, the only time a vector doesn't have direction is when we have no magnitude of 0. Now, this is where I go to my equation sheet. All right, so again, this is the tough part that students have struggle with, is which equation do I use? Now, here's the first step. What am I looking for? Delta D. So my equation has to have delta D in it. If it doesn't have delta D, then I can't use that equation. Now, on this sheet that I have here, right, we have 1, 2, 3, 4, 5 equations, 6, I would actually say, maybe. All right, so when I look at the first equation, this is what I do, process of elimination. It doesn't even have delta D in it. Okay, so I can't use it. Now, here's the other key. Not only does it have to have delta D in it, because that's what we're trying to find, we have to know everything else. All right, so the first equation doesn't even have delta D. Gone, I'm not using it. Second equation does have delta D. but it says I need VI, I need delta T. Okay, I got that. A and delta T squared. I got everything else. All right, so I'm going to use my second equation. So I'm going to write it down here where I've got delta D is equal to VI times delta T plus 1/2 the acceleration delta T squared. All right. Now, when you're working and substituting into your equation, you have to take into account direction. Now, forward for me, now I don't always write this down. I'm going to say is a positive direction, which then makes backwards a negative direction. All right. So you have to denote one direction as positive, the opposite direction is negative. All right. So now that I've done that, delta D, I don't know. All right. I got VI, which is 0, times delta T, which is 5. All right. Then I got plus 1/2. Again, I've said this before, fractions are just divided by questions they're not done with. They just complicate things. So I'm going to switch 1/2 to 0.5. 1 divided by 2. All right. My acceleration is 2.5. It's forward. So I'm going to put a positive 2.5. And I've got my T squared, which is 5 squared. All right. Well, I got delta D by itself already. So I'm just going to use Bedness to figure out my delta D. All right. So 0 times 5 is 0. So there's nothing there. Plus, now again, I got to do Bedness here. So I have to do the exponents first there. So I have to do that 5 squared first. Well, 5 squared, 5 times 5. We got 25. All right, now delta D, I'm going to multiply my 3 numbers there. And let's see here. I multiply my 3 numbers and I get 31.25. Now I'm not done yet because displacement here, what we're finding, is a vector. And my answer is incomplete because number 1, I don't have any units on it, which are important because you'll lose a half mark on the test for no units. And direction, which sometimes you'll lose a full mark. All right, so I got 31.25. Our distance was always in meters here because our acceleration was in meters squared. So we have meters. It was positive 31.25. So that means the distance was forward. Distance or displacement, however you look forward. I hope the speed skater was moving forward. Otherwise, you don't have much chance of winning that race. All right, so there's our first equation. First question. On to example 2. Again, if you have any questions, just speak up. Again, I'm on my cell phone, so I cannot see your chat. Or if I can, it's very small. All right, so example 2. Let's see here. So again, I'm going to follow the same steps. I'm going to write out the information I've got, figure out what equation I got to use, and then substitute in accounting for the sign. So there's our 3 steps. All right, so example 2, getting our information here. All right, so what do we got now? Police car. All right, so a police car, again, I'm going to read the question. A police car is traveling along a highway when a speeding car passes it. Probably not a good idea. The police car then accelerates at a rate of 0.5 meters per second squared east. If the police car accelerates for 10 seconds over a distance of 800 meters, what is the police car's final velocity? What's going on there? Okay, so a police car is traveling. So right there, it's moving. So I don't know what the initial velocity is. Then the speeding car passes it. Now the police car accelerates at a rate of 0.5 meters per second squared east. All right, so there's the first thing. Second sentence, if the police car accelerates for 10 seconds. All right, delta T is 10. All right, over a distance of 800 meters. All right, so if it's accelerating east, then the displacement must also be east. All right, so it's moving along. What is the police car's final velocity? All right. There we go. All right, so I've got my givens down. All right, I didn't see any secret information there. Sometimes there is, because again, the VI, the key there was that it's not zero because the car is traveling. All right, now go to my sheet again, my motion equation sheet. I have to find an equation with VF in it. All right, and then I have to have everything else. So I look at the first equation. It does have VF in it, but it also has a VI in it. I don't have no VI, so I can't use the first equation. I look at the second equation. It doesn't even have VF in it. Can't use it. All right, I go to the third equation. It's got a VF in it, but again, it has a VI in it. Can't use it. Fourth equation. It's got a VF in it, but again, it's got VI in it. I don't have that. So, well, lucky number 5. Let's have a look. It has a VF in it. Good. I need a delta D. I have that. I have delta T, and I need A. Perfect. So the last equation on this sheet, the one at the very bottom in the table, I should say, is the one I'm going to use. So this time I've got delta D is equal to VF delta T minus 1/2 A times delta T squared. All right, there we go. Now, what I'm looking at is direction. Again, I mentioned this before on my compass rose, which we're going to draw more of. Never enter stinky washrooms. I won't say always, 99.9% of the time, I'll say north and east are positive just because they're like that, the same as a graph. All right, so in this case, east is positive for me. All right, so now I'm going to substitute into my equation, keeping into the signs into effect that east is positive. So my displacement here is going to be a positive 800. All right, VF, I don't know. Delta T is 10. All right, let's see here. So then again, I got a minus 1/2. Well, I'm going to convert that fraction into a decimal. Our acceleration is 0.5, and I'm going to put a positive because it is in the east direction. Then I have 10 seconds squared here. That's my... All right, there we go. So I've substituted in my information. All right, so a little bedness here. So let's see here. I have VF times 10. Well, in math and in science, when you have a variable times a number, usually you put the number first. So I'm just changing the way this looks. That's all. All right, then again, on that right side, I'm going to do bedness. So I'm going to do that 10 squared, 10 times 10, which I know is 100. All right, so let's see here. Keep going. I have 800, 10 times VF. All right, let's see here. Now I'm going to do mental math. What's half of 100? 50. What's half of 50? 25. So there should be a minus 25 there. Okay, now I'm going to bring that minus 25 over to the other side. And when it changes sides, it changes sign. So it's going to be 800 plus 25 equals 10 times VF. All right, that's 825, clearly. All right, and then lastly, well, of course, I want to get, well, not lastly, shouldn't say that, but second lastly, I want to get VF by itself, so I'm going to divide both sides by 10. All right, now, I'm going to have VF, let's see, as a numeric number, I get 82.5. All right, but again, when we're doing physics at the end, got to put the units, got to put the direction on it because it is a final velocity vector. All right, our velocity, well, if our time's in seconds, our distance is in meters, acceleration's in meters per squared, it's going to be meters per second. So there's the units. And now finally the direction. As I mentioned, the velocity is positive. I always, 99.9% of the time, say east is positive. So our direction is east. So that is the final velocity, which is crazy because if you change that to kilometers per hour, That's probably 240 kilometers per hour, something like that. So a little bit of a crazy car chase. All right, example 3. Try another one, same idea. So again, you can see I'm writing out while reading the question, figuring out what variables I have and what I'm looking for, finding the equation I got to use, and then substituting in and going from there. All right, so same idea here. Here we go, example 3. All right, so again, I read the question, then go over it again. So let's see here. A freight train traveling at a velocity of 40 meters per second right applies the brakes to slow down to a velocity of 10 meters per second right over a distance of 5 kilometers. How long did it take for the train to slow down? All right, so again, I go sentence by sentence here, or word by word, pretty much for me. A freight train traveling at a velocity of 40 meters per second applies the brakes to slow down to a velocity of 10 meters per second right. So that is telling me I have an initial velocity of 40 meters per second to the right, and we slow down, so that would be our final velocity to 10 meters per second, and we're still going to the right. All right, now, and that happens over a distance of 5 kilometers. So we are still moving to the right because both velocities, final and initial, are right, so our displacement has to be going to the right. And then the last sentence is, how long did it take for the train to slow down? Now, here's a bit of a problem. Before I get to the equations, I got meters per second, kilometers. Our distances always have to be in the same units. All right, so I'm going to rewrite this displacement. And there is, hopefully you know this, but there is 1,000 kilometers, or sorry, 1,000 meters in a kilometer. And so if you have 5 kilometers, you would have, in fact, 5,000 meters. All right, so I got all my distances in the same units, which means because we got meters per second up here, our time is going to be in seconds, which is typical. Now I go to the second step, my equations. So again, I have to have an equation here. I'm looking for the one with delta t in it, and I know the rest of it. So I look at the first equation. It does have a delta t in it, but it also needs acceleration. I don't have that, so I can't use the first equation. The second equation does have a delta t in it, but once again, the acceleration is in there, and I don't have it, so I can't use the second equation. The third equation, or the one there in the middle, let's see, I have a delta t, I have a vi, I have the vf, and I have the delta d. Bingo. It's going to be my third equation this time, so I'm going to write that out, where it is delta d is equal to 1/2 times vi plus vf times delta t. There we go. All right. And in this case, well, look at, I got right. As usual, I always make right positive. So now I'm going to substitute in, given the fact that right is positive. And so my displacement here is 5,000. Go. A positive 5,000, just moving right. 1/2 again, as a fraction, I'm going to put it as 0.5, get that out of the way. All right, VI is 40 meters per second right, so it's going to be a positive 40, just like our final velocity is 10 to the right, so I'll put a positive 10 there, and then I have my delta t. All right, so let's see here. So I got 5,000 here, just simplifying things. Again, Bedmas, I'm going to put that 40 and 10 in brackets. I'm going to put them together, which of course would be 50 delta t. All right, again, simplifying. I can multiply these two. I know what half of 50 is. Don't even need a calculator there. All right, so I got 5,000 equals 25 delta t. Again, I want to get delta t by itself, so I'm going to divide by both sides by 25. And it looks like my delta t, which is the only variable we don't need direction on because time doesn't have direction. Let's see here. Take 5,000 divided by 25. I get 200. And again, you look at our time units. Well, initial and final velocity were meters per second, and so delta t is 200 seconds. And there we go. And again, you don't need direction because there's no direction on time. All right, last one, example 4. All right, so let's see here. What do we got next? A sailboat. All right. All right, so a sailboat accelerates at a rate of 0.25 meters per second squared south to reach a velocity of 6 meters per second south over a distance of 40 meters. What was the initial velocity of the sailboat? All right, so again, I read the question. I'm going through it line by line, word by word. So it starts off, a sailboat accelerates at a rate of 0.25 meters per second squared south. All right, to reach a velocity of 6 meters per second south. So that would be considered my final velocity because we accelerated up to, or the sailboat did, 6 meters per second south over a distance of 40 meters. So let's see here, delta D, if we're accelerating south, that means our displacement, and we're traveling south. We got 40 meters here, south. All right, and then the last sentence says, what is the initial velocity of the sailboat? And there we go. All right, so let's see here. We have to look at the equations. All right, so I end up with looking here. All right, so I need a VI, right? I have to have a VI in my equation and then know everything else. So I look at the first equation. It's got a VI in it. I need a VF. I got that. Oh, I need a delta T. Not going to work, the first equation. Second equation, I got a VI. Again, it needs a delta T, so second equation is not working. Third equation, got a VI. Again, there's a delta T in there. Not happening. All right, fourth equation, it's got a VI. I need VF, I got it. I need a, I got that. And I need a delta D. I got that. Perfect. So I'm on my fourth equation. All right, so let's see here. VF squared equals VI squared. Let's see here, plus 2A delta D. All right, so again, now, south, south, south. Again, 99.9% of the time, I go with north is positive, south is negative. This might be a case where I would say south is positive because they're all south, but I'll stick with what I normally do. All right, so I'm going to go with south is negative here. So when I put a VF squared in here, it's going to be a negative 6 squared. Because again, I said south is negative. All right, I have a VI squared here plus 2 times A. What was A here? 0.25, but it's south. So it's going to be, get rid of that, negative 0.25. And my delta D is 40, so it's going to be a minus 40 because, again, it is south. All right. Now to solve, negative 6 squared, negative times a negative, gives you a positive. All right, now I got to multiply those numbers. So a positive times a negative gives me a negative, but then times a negative is going to give me a positive. And so I multiply those three numbers, and I get a positive 20. All right, I'm going to move that 20 over to the other side. Again, when things change sides, they change sign. All right. And so 36 minus 20 is 16 last time I looked. And now to get rid of the little 2, well, you've had this hopefully before in math class, but you got to square root both sides. And it looks like our VI, the square root of 16, is 4. And because VI is a vector, it's a positive 4 or a negative 4, but we have to analyze it. This is where this formula gets a little bit tricky, as you'll notice there was no vector signs. And so you have to figure out which direction it actually was moving. All right, so in this case, because everything was moving south, our VI is actually 4 meters per second squared to the south. So there's a little bit of a trick with this formula because there is no vector signs, because you cannot square a vector. All right, but you can square a number. So that's kind of a little bit of a trick with that formula in the end. But it looks like this car was moving at 4 meters per second squared, or more 4 meters per second south, upped it up to 6 meters per second. And there we go. So there's our motion equations. Again, I follow the same steps. I read the question. I get my givens down using that formula sheet. I figure out which formula I'm going to use. And again, substituting in, taking into account which direction is positive and which direction is negative. And again, in that first example, I even had you got to watch for some secret information, which we're going to actually talk about more about at 10:30 when we get into the acceleration due to gravity.
I have a question.
Sure, go ahead.
On the right hand